So, welcome again to the new lecture of the course Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap what we have done in the last class. So, in the previous lecture we were looking at temperature dependence of polarization. In a ferroelectric material, and we saw that ferroelectric materials undergo what we call as Curie transition at the temperature Tc, which is called as Curie temperature, and at this temperature when you heat the material transforms from ferroelectric to paraelectric. So, the hysteresis that you see at temperatures lower than Tc, it disappears, and what we have is a more or less like a linear behavior of polarization electric field curve. So, at Tc the structure also changes, from centrosymmetric to non-centrosymmetric non-centrosymmetric to centrosymmetric structure upon heating. And so, this is basically what it is, and we also have this the material follows, the susceptibility follows Curie law. So, the susceptibility shows a behavior as 3 Tc divided by T minus Tc. In many books it is also written as 3 theta divided by T minus theta, or you can also see it is also written as 3 T naught T minus T naught. So, it depends upon the type of book that you are following, but generally this is the behavior that susceptibility follows as a function of temperature. So, basically you can see from here that as T approaches Tc, the susceptibility tends to become very large, and this is also manifested in dielectric constant. So, when you measure the dielectric constant dielectric constant versus temperature shows a maxima abnormal increase at temperature Tc. Okay. So, this is what we did in the last couple of lectures. Today we will look at the thermodynamics of phase transition in ferroelectric material. So, this relies on what we call as Landau theory. So, according to Landau theory, we have seen in the past lecture that the polarization, when you apply, so the polarization can be related to electric field through susceptibility. So, this is susceptibility. So, this is for at least for linear region. Okay. Basically you apply electric field, external electric field leads to change in the charge density in a polar material, that is polarization. And similarly when you apply stress, you can change the charge density. So, di is equal to dijk into x jk, or you can say sigma jk. So, this is what is piezoelectric effect that we have seen. Okay. And then similarly we also saw the pyroelectric coefficient, that was, so change in spontaneous polarization as a function of temperature gives you the pyroelectric coefficient. So, there are many couplings like this. So, basically what we looked at was couplings between electrical, mechanical and thermal properties of dielectric materials, and these are special dielectric. So, So, piezoelectricity is shown by what we call as non-centrosymmetric material, pyroelectricity is shown by non-centrosymmetric and symmetric and polar materials, whereas ferroelectricity is shown by non-centrosymmetric polar and in which polarization is reversible, those kind of materials. Now, what we do is that what we do is that now we first realize what is the free energy. So, free energy of a ferroelectric, let us say, of such a material where these properties are coupled, it is expressed by, so free energy is a function of polarization. So, you can take three components of polarization, Px, Py, Pz, so that is polarization. It is also component of stress, so sigma x to sigma y, sigma z. So, basically instead of writing this, I can just write function of Pi. So, where Pi could be 1, 2, 3 and then you have sigma ij. So, stress tensor and then of course temperature. Okay. And then free energy is also affected by what we call as electric. So, now this is polarization is the generally what we measure after applying electric field. Stress is something which you can apply or measure after you have application of electric field or application of strain, then you have thermal response. So, basically when we apply electric field we can measure polarization, when we apply stress we can measure a strain or vice versa, and similarly when we apply electric field we can measure a stress, or when we apply stress we can measure the polarization and so on and so forth. So, this is how it sort of couples these properties. So, you can do Legendre transform to relate it to really the stimuli. So, stimuli in this case would be E, so this is epsilon, sorry, E, sigma and temperature, right. And you can write this in terms of E sigma and T, or you can write this in terms of P epsilon and T, or it could be Xij or it could be capital Xij, right. So, there are various ways of writing this free energy equation that we saw in earlier lecture. So, now let us write a little bit detailed free energy equation. So, let us say we write elastic Gibbs free energy in terms of variables temperature, stress, x and polarization. So, now we talk of ferroelectrics mostly in terms of polarization instead of D, the charge density, because polarization and D are interchangeable. So, instead of D we will use P, which is more common quantity, and we assume very small changes in T, X and P. Okay. So, the free energy expression turns out to be, so free energy expression G1 can be written as G naught T. This is equal to del of G1 del T into delta T plus del of G1 del Xij plus del of G1 into dPi. So, this is the first order change that you make on the basis of temperature, the stress and the polarization. Okay. Now you need to take the second order terms. So far we did not consider the first second order terms, but we need to do the second order terms, which is nothing but Taylor expansion. So, the second order terms are 1/2 del 2 G1 by del T square into delta T square plus half of del 2 G1 divided by del Xij del XKL divided by Xij into XKL plus half of del 2 G1 del of Pj into del of Pi into Pj. So, this is the second order term for temperature, stress and polarization. Now, we look at the interdependence of these. If we go to del 2 G1 del T del Xij. So, this becomes delta T into Xij. So, this is the first interdependence of. So, you have first derivative del G upon del X, and after that you make a change in temperature, and then, so this is the interdependent term. Then second interdependent term will be, it could be between temperature and polarization. So, this could be delta T into Pi, right, and then third term is del 2 G1 del Xij del Pk, and this is Xij into Pk, and then we can have various other terms. We have alpha delta T cube, which is the volume expansion term, and then we have beta Ijk Pi Pj Pk, this is the third order term. So, now we take the third order term. So, this is the third order term, this is the third order term, and then we take gamma Ij Kl Mn Xij Xkl into Xmn plus other higher order terms. So, this is a massive equation. So, basically what are these terms? These terms are alpha Ijk. So, alpha basically alpha, beta Ijk and gamma, beta Ijk, gamma Ijk, Lmn. These are third order coefficients, right, of derivatives with respect to temperature, with respect to stress, and with respect to polarization, right. These are the three. So, here we assume that G, the free energy, describes both polar and non-polar phases. So, polar will mean that it is ferroelectric phase, and non-polar will mean paraelectric phase. So, this is T less than Tc and this is T greater than Tc, right. And then all the coefficients, as we see, they are tensors, are vectors slash tensors depending upon the coefficients, okay. And of course, if non-polar force, if non-polar what will happen, if non-polar phase is centrosymmetric, which means displacement in positive direction will cancel the displacements in negative direction. As a result, all the odd terms will cancel out each other. So, all the okay. So, we imagine that our ferroelectric is, assume that ferroelectric is uniaxial, which means polarization either is in this direction or in that direction. There are no multi-component polarization vectors which might complicate the situation. So, if this is P plus, this will be P minus, and the field is applied parallel to the polarization, just for the sake of simplicity, okay. So, basically we want to write a expression for free energy of a crystal, and whatever we do when we want to calculate the value of various independent variables, we need to minimize the free energy with respect to that variable, right. When you want to calculate something at equilibrium, then free energy value must be minimum for that particular variable, just like we do it in defect concentration, any other thing. The free energy should get minimized for that particular variable. So, now we would like to expand this free energy equation in terms of polarization only, and we will ignore other terms. So, we will just look at the polarization for a uniaxial ferroelectric term, ferroelectric, and ignore the stress field. So, we write G in terms of P only, ignore stress fields, okay, and this is okay because you have a uniaxial ferroelectric. So, we are not considering any other directions as such, and it is an unstrained crystal. So, let us say we write the ferroelectric Gp as the energy as becomes half of A P square 1 over 4 Bp to the power 4 plus 1 over 6 Cp to the power 6. So, we write this expression for free energy, that is in terms of polarization only. Gp is equal to half of Ap square plus 1 over 4 Bp 4 plus 1 over 6 Cp 6 plus and then minus Ep, which is the product of electric field and polarization, which is the depolarizing energy for a ferroelectric, because in ferroelectric when you have polarization aligned in one direction, then there is a opposing force which is the depolarizing energy which wants to depolarize the material, and we take even powers only, because energy is same for plus Ps or minus Ps direction, and the other term cancel out each other as we just discussed earlier for a non-polar centrosymmetric phase. So, here E as we see is the electric field, and A, B and C are constants which are function of temperature, they are temperature dependent. Okay. So, this is a simplified equation. Of course, you can write a complicated equation, but you can see that we have written that equation just in terms of polarization, ignoring the stress field. And let us say you want to now find out where is the minima of energy with respect to polarization. So, equilibrium with respect to polarization is achieved by minimizing the free energy. So, we say that del of G P versus del P as at a constant temperature is equal to 0. Okay. So, if we do that, then this expression can be A of P plus B of P cube plus C of P5 plus minus of E is equal to 0. So, assuming that first, if A, B, C are all positive, okay, because we do not know the value of A, B, C yet. So, we are saying that right now, assuming that if A, B, C are all positive, then of course, you can see that and let us say if E is equal to 0, then we can say that AP plus BP cube plus CP5 is equal to 0, ignoring higher terms. Okay. And that is okay if we assume the change in the polarization is small, and as a result higher order terms will not play a significant role. So, if that is true, if A, B, C are all positive and E is equal to 0, then we can clearly see that P is equal to 0 is one root, right. Right. So, at P is equal to 0, there is certainly one minimization that will occur. So, that is first lesson that we learn from this exercise. So, basically we can say that at a temperature, so now when are these conditions met? These conditions A, B, C are positive are met. So, when T is greater than a critical temperature Tc and A is greater than 0, simultaneously V is greater than 0, C is greater than 0, in that case the free energy shows, so this is G versus P. So, at P is equal to 0, we have a free energy minimum. So, basically for this condition we represent the material as material being material is in paraelectric state, and what it means is that when E is equal to 0, P is also equal to 0, and that is what it meant for a paraelectric state. This was our plot. So, this is P, this is E, saturates of course, but at P is E is equal to 0, the P is equal to 0, that is what a root is, and that is where the free energy minimum occurs. So, this basically suggests that at E is for A greater than 0, B greater than 0, C greater than 0, at T greater than Tc, the material is in paraelectric state with polarization being equal to 0 as a root. So, now let us say in the above derivation that we did, we took AP plus BP cube plus CP5. Now, let us say E is not equal to 0. Okay. Now, let us say assume that E is not equal to 0. If E is not equal to 0, then we know that AP, then we said that del G by del P is equal to 0 at constant temperature. Okay. So, AP plus BP cube plus CP5 minus E was equal to 0, right. This was the expression that we have. Now, let us say we ignore third order and higher terms for a small polarization. Okay. Then we can write AP minus, basically we are saying if P is small, right. So, AP minus E is equal to 0. What it means is that we have A being equal to E divided by P, or we can say A inverse is equal to P divided by E. And what is P divided by E? P divided by E is nothing but the susceptibility. So, this is susceptibility of a ferroelectric for a linear in the linear region, that is chi is equal to P divided by E, which is nothing but A inverse. So, now on the other hand, so this is the first part of it. Now, on the other hand, if we say, if we assume A less than 0, but B and C greater than 0, and what did we say earlier? A, B, C all are temperature dependent. So, which means something has happened to temperature because A has changed its sign. So, if A is positive for T temperature greater than for T being greater than Tc, then T must have gone below Tc for A being less than 0. So, this condition is valid for T less than Tc. So, in this case, if A is less than 0 and B and C are greater than 0, then there should be, so not only P is equal to 0 is a root, there should also be a root at P that is non-zero. So, we must have a root at P not equal to 0, right. There should be some finite value. So, this is expressed in this form schematically. We will do a detailed analysis in a little while. So, this is G and this is P. So, we have a root here, that is minus PR, this is a plus, just write minus P and plus P, and this is a maxima that we get at. So, I mean this is maxima or minima, we did not define it, right. I mean, so here we are, what we are getting is a maxima in G at P is equal to 0 and minimas in G at two values, that is plus P and minus P, and this condition is defined for T less than Tc, and this is for A being less than 0 and B, C being positive. And basically this is manifested in terms of in this fashion. So, if you now put the two curves together, okay, if you now put the two curves together, let us say we plot G as a function of polarization, and this is polarization. The first thing that we drew was like this, right. This is G, this is the curve at T greater than Tc when we have one root. What happens when you decrease the temperature at T less than Tc? We have a situation which is like this, which is at T less than Tc. So, at this temperature A is greater than 0, at this temperature A is less than 0, and B, C being equal to 0 for all temperatures. So, in between what happens at T is equal to, which means if A is changing its sign, it must go through 0, right. At this temperature is greater than 0, at this temperature is less than 0, it makes sense that A will go through sort of a change of sign at T is equal to Tc, where A is equal to 0, and that is where free energy shows a shallow sort of minima. So, there is a transition that takes place in the nature of free energy curve. This is, so just a little perturbation below C will give you two minimas like this. So, this is reflected in terms of polarization. So, if you plot now polarization as a function of temperature, the polarization decreases gradually at a temperature called as Tc. Okay. So, below Tc you have finite polarization, either you will have plus P or minus P, it is a uniaxial ferroelectric and both the states are equal. So, you can write this as mod P, okay. And you can also plot another parameter, that is susceptibility. So, susceptibility we saw that it varies as, so if you look at this expression, it varies as P over E, right. But in the previous analysis that we did, we will do temperature dependent analysis and we will see that susceptibility 1 over chi varies in this fashion. So, it has certain dependence at temperature above Tc, 1 over chi decreases to 0 at Tc and then again increases. And in terms of dielectric constant, what it would mean is that if you plot dielectric constant, let us say epsilon r, you will have a divergence of dielectric constant at this value, right, or even susceptibility, right, because chi is equal to epsilon r minus 1. So, this kind of phase transition where susceptibility, where there is a gradual change in the free energy plot, where the polarization is dropping gradually, where susceptibility goes to a minimum 0 and then again increases, or sorry, 1 over chi, as you decrease the temperature, first decreases and then increases, and at Tc it goes to equal to 0. This kind of transition where there is no discontinuity in the polarization, in the susceptibility, and there is not a sudden jump in polarization. This kind of transition is called as second order phase transition. And if you calculate in this case, you will not have a discontinuity in entropy or specific heat when you calculate for these materials. So, these are second order continuous phase transitions where susceptibility does not change abruptly at the transition, or order parameter, polarization is called as order parameter. The order parameter does not abruptly become equal to 0, rather it goes to 0 gradually, okay. And this is what it means in terms of, since what happens in this case is the polarization can be related to entropy in terms of, so I will not do the analysis or detailed analysis, but you can relate the entropy as minus of del G by del T, right, and then you can calculate delta S as being equal to minus of half P square del A by del T, and this is also continuous. So, when this is continuous, which means the phase transition is second order. If there is a discontinuity you see, then it is a first order phase transition. If it is continuous, then it is a second order phase transition. So, this is basically a second order phase transition. It is seen in materials such as Rochelle salt, KH2PO4 etc. Okay. So, what we will do is that we will stop here. We will look at the analytical treatment of this phase transition in the next lecture, and we will also follow up with the discussion on the first order phase transition. Okay. Thank you.